Wind energy. Course outline. Introduction to wind energy. The history of wind power. How wind turbines work. Types of wind turbines. The science behind the wind. Wind farms and their impact. Pros and cons of wind energy. Global wind energy usage. Innovations in wind technology. Wind energy and the environment. Careers in wind energy. The future of wind power. What you can do, supporting renewable energy. Part 1. Introduction to wind energy. Wind energy is one of the fastest growing sources of renewable energy in the world. It's clean, sustainable, and abundant. As the world grapples with the consequences of climate change and the environmental cost of fossil fuels, wind energy has emerged as a key player in the transition to a greener future. But how does it all work? How can something as invisible and unpredictable as the wind be turned into electricity that powers our homes, schools, and businesses? This course explores the fascinating world of wind energy, how it's captured, converted, and used to meet the world's growing energy demands. Whether you're a curious student, a budding engineer, or simply someone who cares about the environment, this course will guide you through the exciting journey of wind power, from ancient windmills to massive wind farms that stretch across oceans. Part 2. The history of wind power. Long before wind turbines dotted the modern landscape, humans were harnessing the power of the wind in creative and essential ways. The history of wind energy is a story of innovation, exploration, and the pursuit of sustainability, stretching back thousands of years. Ancient beginnings. The earliest known use of wind power dates back to around 5000 BCE in Egypt, where people used sailboats to navigate the Nile River. These simple sails captured wind and turned it into movement, making transportation faster and more efficient. By 200 BCE, wind-powered water pumps and grain mills were being used in Persia, modern-day Iran. These early windmills were vertical in design, unlike the towering turbines we see today. Their sails spun on a vertical axis, using the desert breezes to grind grain or pump water for agriculture. Windmills in medieval Europe. During the 12th century, wind technology made its way into Europe. The windmills built in the Netherlands and England were iconic in appearance, wooden structures with large horizontal sails mounted on a rotating cap that allowed them to face the wind. These mills played a crucial role in farming societies, grinding flour and draining wetlands to create farmland. In the Netherlands especially, windmills became not only a tool, but a symbol of cultural identity and innovation. The Dutch perfected the use of wind power for land reclamation, building a network of mills that helped shape the country's geography. The industrial shift. With the onset of the Industrial Revolution in the 18th and 19th centuries, steam engines and fossil fuels began to replace traditional windmills. Wind energy took a backseat as coal and oil powered factories, transportation, and homes. Yet in rural areas, especially in the United States, wind-powered water pumps remained important for farmers and ranchers, particularly in places without access to electricity. The birth of modern wind turbines. The first attempt to generate electricity from wind came in 1887, when Professor James Blythe of Scotland built a wind turbine to power his holiday home. Around the same time, Charles F. Brush in the United States developed a larger wind-powered generator in Cleveland, Ohio. These early inventions were the ancestors of today's wind turbines. In the 20th century, particularly after oil crises in the 1970s, interest in alternative energy sources grew. Governments and scientists began investing in wind energy research, leading to the development of more efficient turbine designs. Wind energy in the 21st century. Today, wind energy is a global industry. With modern turbines that can stand over 800 feet tall and generate power for thousands of homes, wind farms are transforming skylines and reducing our reliance on fossil fuels. From its humble beginnings in ancient Persia to the massive offshore wind farms of today, Wind energy has evolved tremendously, but the basic idea remains the same, using the wind to do work. And now, more than ever, it's becoming clear that the wind might just hold the key to a cleaner, more sustainable future. Part 3: How wind turbines work. At first glance, a wind turbine might look like a giant fan spinning in the sky, but it's actually doing the opposite. Instead of using electricity to make wind, like a fan does, a wind turbine captures the wind's energy and turns it into electricity. Let's break down how this incredible transformation happens. The basic principle: kinetic energy to electricity. Wind is moving air. And moving air carries kinetic energy, the energy of motion. A wind turbine captures this kinetic energy using its blades and converts it into mechanical energy. That mechanical energy is then converted into electrical energy using a generator. The process goes like this: wind right-pointing arrow blade movement, right-pointing arrow shaft rotation, right-pointing arrow generator, right-pointing arrow electricity. Key components of a wind turbine. To understand this transformation better, let's look at the main parts of a modern horizontal axis wind turbine, the most common kind. 1. Blades. Most turbines have 3 blades, although some models have 2. These blades are shaped like airplane wings, using a design called an airfoil. As wind moves over the curved surface, it creates lift, a force that causes the blades to turn. 2. Rotor. The blades are attached to a hub, and together they make up the rotor. When the wind blows, the rotor spins. 3. Nacelle. This is the big box behind the blades. It contains all the machinery that transforms mechanical energy into electricity, including main shaft, connected to the rotor; gearbox, to increase rotation speed; generator, converts movement into electricity; brake, for safety, stops the rotor if needed. 4. Gearbox. The blades turn relatively slowly, but electricity needs a high-speed rotation. The gearbox increases the shaft speed from around 10 to 20 rpm, rotations per minute, up to around 1,500 rpm for the generator. 5. Generate. This is where the magic happens. The generator uses magnetic fields and coils of wire to produce electricity from the rotating motion. It works similarly to the alternator in a car. 6. Tower. Turbines are placed on tall towers, usually 80 to 120 meters, 260 to 390 feet, high, because wind speeds are stronger and more consistent higher above the ground. 7. Anemometer and wind vane. These tools sit on top of the nacelle. Anemometer measures wind speed. Wind vane shows the direction of the wind. The turbine uses this data to position itself correctly into the wind. 8. Yaw mechanism. This system turns the nacelle so that the blades always face the wind. Without this adjustment, the turbine wouldn't operate efficiently. From turbine to grid. Once the electricity is generated, it travels down cables through the tower to a transformer which adjusts the voltage. From there, it's sent to the power grid, where it can be distributed to homes, schools, factories, and more. Small versus large turbines. Not all wind turbines are giant machines on wind farms. Small wind turbines can be installed for individual homes or farms, often producing enough electricity for just one building. The mechanics are the same but on a smaller scale. Efficiency and challenges. Modern turbines are highly efficient, but they don't capture all the wind's energy, usually around 35 to 45% depending on design and conditions. The Betz limit, a physical principle, says no wind turbine can capture more than 59.3% of the wind's energy, no matter how advanced it is. Turbines also have to shut down in very high winds to avoid damage, and they only work well in places with consistent strong wind. Wind turbines are engineering marvels, silent workers that stand tall, catching the breeze and sending clean energy across the wires. In the next part, we'll explore the different types of wind turbines and how they're used in different environments. Part 4. Types of wind turbines. Not all wind turbines are built the same. Depending on their size, location, and purpose, wind turbines come in different shapes and designs. While the towering three-blade machines are the most familiar, there's a surprising variety in how humans have learned to capture the wind's energy. In this part, we'll explore the two main categories of wind turbines and their subtypes. 1. Horizontal axis wind turbines, HAWTs. These are the most common wind turbines in the world, and the ones most people think of when they picture a wind farm. Key features. Rotor shaft is horizontal, parallel to the ground. Blades face directly into the wind. Usually mounted on tall towers. Advantages. High efficiency in open areas with consistent wind. Widely researched, mature technology. Easier to scale for large energy production. Disadvantages. Requires complex yaw systems to turn and face the wind. Needs a lot of space. Tall towers can be visually intrusive or face zoning restrictions. Common uses. Utility-scale wind farms onshore and offshore. Community energy projects. 2. Vertical axis wind turbines, VAWTs. VAWTs spin like a carousel rather than a propeller. Their vertical design means they don't need to face the wind to work, which makes them ideal for unpredictable or turbulent wind conditions, like in cities or near buildings. Key features. Rotor shaft is vertical, perpendicular to the ground. The wind can blow from any direction. Advantages. No need for yaw mechanisms. Can be installed closer to the ground. Better suited for urban or built environments. Disadvantages. Generally less efficient than HAWTs. Difficult to scale up for large power production. Some designs experience more mechanical stress. Common VAWT designs. A Darius turbine. Shaped like an egg beater or curved blades. Invented by Georges Darius in the 1930s. Efficient, but mechanically complex. B. Savonius turbine. Uses scooped blades that catch the wind. Simple and robust, though not very efficient. Commonly used in small-scale or demonstration projects. 3. Offshore versus onshore wind turbines. Another way to classify turbines is by where they are installed. Onshore wind turbines. Built on land. Easier and cheaper to install and maintain. Limited by land availability and public acceptance. Offshore wind turbines. Installed in oceans or large lakes. Higher, more consistent wind speeds. Can be much larger in size. More expensive to build and maintain but offer greater energy potential. 4. Floating wind turbines. A newer technology, floating turbines are designed for deep waters where fixed foundations aren't practical. They're anchored by cables and can float like buoys, following the motion of the sea. These have huge potential for expanding wind energy into new areas. 5. Small wind turbines. Not every wind turbine needs to power a city. Small turbines, usually under 100 kilowatts, are often used for homes or farms, remote facilities, off-grid systems. They're often simpler in design and may include battery storage. Choosing the right turbine. The best type of wind turbine depends on the location, wind conditions, space and energy needs. For example, rural areas with open land. HAWTs are ideal. Windy coastlines with deep water. Floating offshore turbines. Urban rooftops or tight spaces. VAWTs might make more sense. Wind turbines, like wind itself, come in many forms. And as technology continues to evolve, we're discovering even more innovative ways to adapt turbines to different environments and energy goals. Part 5. The science behind the wind. Before we can harness the wind's energy, we need to understand where wind comes from, how it behaves, and what factors affect its power. The science of wind might seem invisible, but it's driven by a mix of natural forces that shape everything from gentle breezes to powerful gusts. Let's break it down. What is wind? Wind is simply moving air. It happens when the sun heats the earth unevenly, causing temperature differences across the planet. These temperature differences lead to changes in air pressure, and when high-pressure air moves toward low-pressure areas, voila, we get wind. In short, wind equals air moving from high pressure to low pressure. Why the Earth heats unevenly? The equator receives more direct sunlight than the poles, so it's warmer. Land heats up faster than oceans during the day and cools down faster at night. Mountains, forests, cities, and open plains all absorb and reflect sunlight differently. These differences create pressure gradients, which in turn create wind patterns. Wind is nature's way of trying to balance out these temperature and pressure differences. The role of the sun. The sun is the ultimate source of all wind energy. Think of it like this. Right-pointing arrow heats the earth, right-pointing arrow creates pressure differences, right-pointing arrow moves air, right-pointing arrow creates wind, right-pointing arrow powers turbines. Without the sun there would be no wind, and no wind power. Global wind patterns. The Earth's rotation, shape and tilt all play a role in global wind movement. Coriolis effect. Because the Earth rotates, air moving in a straight line appears to curve. This is known as the Coriolis effect, and it causes winds to curve right in the northern hemisphere, winds to curve left in the southern hemisphere. Jet streams. These are fast-moving air currents high in the atmosphere, influencing weather patterns and local wind conditions. Trade winds, westerlies, polar easterlies. These are large, stable wind belts around the globe. For example, trade winds blow toward the equator. Westerlies blow from west to east in the mid-latitudes, where most wind farms are. Polar easterlies are cold winds near the poles. Local wind patterns. Wind conditions can vary greatly, depending on local geography and weather. Here are a few key factors. Topography. Wind speeds increase on hills and ridges. Mountains can funnel wind through valleys. Obstacles like buildings and trees slow down or redirect wind. Sea breezes and land breezes. During the day, land heats faster than water, drawing cool air in from the sea breeze. At night the opposite happens, land breeze. Thermals. When warm air rises over land, cooler air rushes in to replace it. This vertical movement of air is common in sunny areas and can affect wind turbine performance. Measuring wind for energy. To generate wind power, we need to know wind speed, measured with anemometers. Wind direction, measured with wind vanes. Wind consistency, how stable the wind is over time. The ideal wind speed for most turbines is between 12 to 25 miles per hour, 5.5 to 11 meters per second. Too slow, and the turbine won't spin. Too fast, usually above 55 miles per hour or 25 meters per second, and the turbine shuts down to avoid damage. Wind power equation. The power in the wind increases with the cube of wind speed. That means, if wind speed doubles, the power increases by 8 times. This is why choosing the right location for a wind turbine is critical. A slightly windier site can produce a lot more energy. Turbulence and wind shear. Turbulence. Irregular chaotic wind flow often caused by buildings or trees. Bad for turbines. Wind shear. Change in wind speed or direction with height. Wind is usually faster higher up, which is why turbines are mounted on tall towers. Understanding the science behind the wind helps us find the best places for turbines, design them more efficiently, and predict how much energy they'll generate. Wind isn't random, it's a powerful natural system that follows clear rules. And when we work with those rules, we can turn air into energy. Part 6. Wind farms and their impact. A single wind turbine can generate enough electricity to power hundreds of homes. But when turbines are grouped together in large numbers, They form wind farms, vast power plants that turn open skies and breezes into clean, renewable energy. These farms are a cornerstone of the global shift toward a more sustainable energy future. In this part, we'll look at how wind farms are built, where they're located, how they work together, and what kind of impact they have on the land, wildlife, and people around them. What is a wind farm? A wind farm is a collection of wind turbines that are installed in the same area and connected to a common power grid. They can range in size from just a few turbines to hundreds, spread out across thousands of acres of land or sea. Types of wind farms. Onshore wind farms, located on land, often in rural or agricultural areas. Offshore wind farms, built in bodies of water, typically oceans or large lakes. Nearshore or coastal wind farms, built close to the shore, combining features of both onshore and offshore. How wind farms work. Each turbine in a wind farm captures the wind and converts it into electricity independently. But together, they are strategically positioned and controlled to maximize energy output and efficiency. Key considerations in wind farm design. Turbine spacing. Turbines must be spaced out to avoid the wind shadow, turbulence, created by nearby machines. Topography. Hills, ridges, and flat plains all affect wind flow. Wind direction. Farms are laid out to face prevailing winds. Grid connection. All turbines are wired into a central substation that feeds into the larger electrical grid. A typical modern wind turbine in a large farm can produce between 2 to 5 megawatts (MW) of power. Multiply that by dozens or hundreds of turbines, and the output becomes truly massive. Land use and coexistence. One of the most beneficial aspects of onshore wind farms is that they don't use up the land the way fossil fuel operations do. In agricultural areas, farmers often lease parts of their land for turbines, while continuing to grow crops or raise livestock. On average, only 1 to 2% of the land area in a wind farm is actually taken up by turbines and infrastructure. The rest remains usable. Offshore wind farms, big power at sea. Offshore wind farms have become increasingly popular because wind speeds are stronger and more consistent over water. There's less visual and noise impact for people on land. Turbines can be larger than land-based models. Challenges include high costs of installation and maintenance, harsh weather and corrosion, complex transmission back to the mainland grid. Still, countries like the UK, Germany, China, and Denmark are investing heavily in offshore projects to meet their energy goals. Environmental impact. Like all energy sources, wind farms have an impact, but it's relatively low, especially compared to fossil fuels. Positive impacts. No air or water pollution. No greenhouse gas emissions. Low water usage compared to nuclear or coal plants. Concerns and mitigation. Wildlife, especially birds and bats, collisions can occur, though newer turbine designs and better placement reduce risks. Noise. Turbines produce a soft whooshing sound. It's generally minimal, but can be a concern if turbines are too close to homes. Visual impact. Some people find turbines disruptive to scenic views, especially in rural or coastal areas. Construction disruption. Building access roads and turbine pads can disturb habitats, though many effects are temporary. With careful planning and technology, most of these concerns can be managed. Economic and social benefits. Wind farms create jobs in construction, operations, and maintenance. Income for landowners through lease agreements. Tax revenue for local governments and services. They also lower energy costs over time by reducing reliance on imported fuels and shielding consumers from fuel price volatility. Community wind projects. Some wind farms are developed not by large corporations, but by communities, cooperatives, or local governments. These projects allow local people to own part of the energy infrastructure, receive direct benefits from clean power, strengthen energy independence. This model has been especially successful in parts of Europe and is gaining traction globally. Conclusion. Wind farms are more than just a collection of spinning blades. They're a clean energy solution that balances power production with sustainability. Whether on land or at sea, they represent a smart and scalable path toward reducing our carbon footprint. Part 7. Pros and cons of wind energy. Wind energy has surged into the spotlight as a clean, renewable, and increasingly cost-effective solution to the world's growing energy needs. But like any technology, it comes with both advantages and drawbacks. In this part, we'll take an honest look at the benefits and challenges of wind power so you can see the full picture. Advantages of wind energy. 1. Clean and renewable. Wind energy produces zero emissions once the turbines are up and running. It doesn't burn fuel, release greenhouse gases, or pollute water supplies. As long as the wind blows, we can keep generating electricity. 2. Low operating costs. After installation, wind turbines are relatively inexpensive to operate. There's no need to purchase fuel, and maintenance costs are modest compared to fossil fuel plants. 3. Scalable and flexible. Wind energy can work at various scales. Massive utility-scale wind farms. Community wind projects. Single turbines for homes or farms. 4. Creates jobs. From manufacturing blades to maintaining turbines, wind power creates employment across sectors: engineering, logistics, construction, and more. 5. Energy independence. Wind energy reduces dependence on imported fossil fuels, increasing energy security for many countries and regions. 6. Land use compatibility. Wind turbines take up very little actual ground space. Farmers and ranchers can continue using the land for agriculture while earning income from turbine leases. 7. Fast installation. Compared to other power plants, wind farms can be built and begin generating power relatively quickly, especially onshore projects. Disadvantages of wind energy. 1. Intermittency. Wind doesn't blow all the time. That makes wind energy variable and sometimes unpredictable, which can cause challenges for grid stability. Solution: backup systems, energy storage like batteries, and a diversified energy mix. 2. Visual and noise impact. Turbines are tall and visible. Some communities consider them an eyesore or complain about the low-level noise they produce. 3. Wildlife concerns. Birds and bats can collide with turbine blades. However, research and smarter siting can reduce this impact significantly. 4. Upfront costs. While wind energy is cheap to operate, the initial investment for turbines, land, and grid infrastructure is high. 5. Transmission challenges. Wind farms are often located in remote, windy areas. Getting that energy to cities requires building new transmission lines, which can be costly and time-consuming. 6. Land and environmental disruption. While minimal, the construction of wind farms still involves land use, access roads, and concrete foundations that can disrupt habitats during installation. 7. Material use and end-of-life concerns. Turbines are made from steel, fiberglass, and rare earth metals. Recycling blades at the end of their lifespan is still an evolving challenge. Weighing the trade-offs. Every energy source has pros and cons. What makes wind energy stand out is its potential to reduce emissions, stabilize energy costs, and grow alongside new technologies like battery storage and smart grids. As innovation improves turbine design, forecasting tools, and grid systems, many of today's downsides are becoming more manageable. In a balanced energy future, wind plays a critical role, not alone but alongside solar, hydro, and other renewables. Conclusion. Wind energy isn't perfect, but its strengths are powerful. As the world races to cut carbon emissions and move away from fossil fuels, wind stands tall, literally and figuratively, as a vital part of the solution. Part 8. Innovations and the future of wind energy. Wind energy has come a long way since the days of simple windmills. Today's sleek, high-tech turbines are the result of decades of engineering and environmental research. But the journey is far from over. In this part, we'll explore the cutting-edge innovations transforming wind energy, emerging trends shaping the future, and how this technology might evolve in the decades to come. 1. Bigger, smarter, stronger turbines. Turbines are getting taller, more efficient, and more powerful. Mega turbines. Modern offshore turbines can now reach 15 megawatts per unit, with rotor diameters over 250 meters. The trend is toward fewer turbines that can generate more power, reducing infrastructure needs and costs. Advanced materials. New composite materials are making blades lighter and stronger, which improves performance and longevity. Recyclable blade materials are also in development to address end-of-life challenges. Digital twin technology. Digital replicas of turbines are used for real-time monitoring and predictive maintenance, reducing downtime and increasing lifespan. 2. Floating wind turbines. The next frontier for offshore wind is deep water, where fixed-bottom foundations aren't feasible. Floating platforms. These turbines are anchored to the seabed with cables and can float like giant buoys. Allows access to stronger, more consistent winds in deep ocean areas. Opens up new geographic markets, like Japan, California, and parts of the Mediterranean. Challenges. Higher costs for now. Engineering stability in rough seas. Complex anchoring and cabling systems. But despite challenges, floating wind is expected to play a major role in global energy production by 2035. 3. Vertical axis wind turbines revisited. New interest is forming around vertical axis wind turbines, VAWTs, especially for urban areas with turbulent wind. Small-scale installations on rooftops or streetlights. Modern VAWTs feature improved aerodynamics, quieter operation, and lower maintenance. 4. Artificial intelligence and smart grids. AI in wind energy. AI helps predict wind patterns, optimize turbine performance, and improve maintenance scheduling. Smart algorithms can adjust blade pitch and yaw in real time for maximum efficiency. Smart grids. Wind energy is variable, but smart grids can manage that variability by balancing energy from multiple sources. Paired with energy storage, wind farms can now provide on-demand electricity even when the wind isn't blowing. 5. Energy storage solutions. One of the biggest barriers to 100% renewable energy has been storage. But that's changing. Battery storage. Lithium-ion and flow batteries are being deployed next to wind farms to store excess energy. This smooths out supply, enhances grid stability, and supports demand during peak times. Other storage tech. Hydrogen production, using excess wind energy to make green hydrogen. Compressed air and gravity-based systems. 6. Modular and portable wind power. New designs are focusing on portable, easy-to-assemble turbines for disaster relief, remote villages, military and research outposts. These small, robust systems bring clean energy to areas without traditional infrastructure. 7. Community-driven models. The future of wind isn't just technological, it's social. Community wind projects allow locals to own part of the infrastructure. Keep energy dollars in the local economy. Increase public support for renewables. Crowdfunding co-ops and local partnerships are making wind power more democratic and accessible. 8. A role in climate solutions. Wind power will be critical to achieving net zero emissions and meeting climate targets. Combined with solar hydro storage and carbon capture, wind helps decarbonize electricity, power electric vehicles and heating, Reduce reliance on fossil fuels in every sector. The International Energy Agency predicts wind could supply up to 35% of global electricity by 2050. Conclusion. The future of wind energy is bold, innovative, and essential. With smarter machines, deeper installations, better storage, and more inclusive models, wind is set to become a backbone of global energy and a powerful ally in the fight against climate change. Part 9. Wind energy around the world. Wind energy is truly a global movement. From towering turbines along the coasts of Denmark to vast wind farms across the American Midwest and China's desert megaprojects, countries around the world are tapping into the power of the wind